Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 11. Gauss-Chebyshev Method and Quadrature. The Gauss-Chebyshev method is a part of the broader class of Gaussian quadrature methods, which approximates the definite integral of functions having discontinuities in both the lower and upper integral limits. The method approximates an integral using a weighted sum of function values at specific integration points or nodes within the integration domain and associated weights. The Gauss-Chebyshev quadrature handles type 2 improper integrals of the following standard form, where fx is itself bounded, and the cause of singularity at x equals plus and minus 1 is due to the square root term in the denominator. The integral is expressed as a weighted sum, where n is the number of quadrature points, xi and wi are the abscissas and corresponding weights, referred to as Gauss-Chebyshev quadrature, and Rn is the global error, which is defined as follows, where the upper or lower error bounds for a Cn estimate can be determined from the absolute maximum and minimum values of 2nth derivative of f over the domain from -1 to 1. The abscissas for an endpoint quadrature are the zeros of the Chebyshev polynomial of the first kind, which are symmetrical about x equals 0, and nth-order polynomial is defined as follows. Fortunately, unlike other quadrature methods, the abscissas and weights of an endpoint Chebyshev quadrature can be easily calculated with the following explicitly determined expressions. Consider the following integral in which the integrand has singular points at both limits of the integral. The integral is transformed to standard Gauss-Chebyshev form as follows. The integral can then be approximated by the weighted sum as follows, where ui and wi are the set of quadrature for the standard form. Xi is computed as follows, and the weights remain unaltered. And the global error becomes. Some integrals may not be entirely in standard Gauss-Chebyshev form. That is, an integrand may only have a discontinuity at either x equals a or x equals b. For example, these integrals can be expressed in the standard Gauss-Chebyshev form as follows. The advantages of the method are: high-order accuracy can be achieved using Cn approximation. It is well suited for integrals with singularities at the endpoints. They converge very quickly for relatively small n if the integrals are in standard forms. The disadvantages of the method are: the theoretical error estimation procedure is not an easy task. They are not suitable for discrete or non-analytic functions. It is only suitable for 1 over the square root of 1 minus x squared as a weight function. Highly accurate quadrature sets are required to compute integrals with high accuracy. Consider the following integral with singularities at both endpoints. Investigate the convergence of the integral using the Gauss-Chebyshev method for increasing values of n. Here, J0x is the Bessel function of the first kind. The integral is approximated as follows. The given integral is basically in the standard form from a equals minus pi to plus b equals pi. The abscissas are pi times ui, the weights are pi over n, and fx is sine squared x, and ui are defined as. The global error for this problem takes the following form. The C4 approximation is written as follows. Then we calculate the abscissas, UIs, and tabulate them. Modified abscissas, XIs, are also computed and tabulated. Note that fx is sine squared x, and the weights are independent of subscript I, so we can keep the weights outside the summation sign. Next, all we need to do is sum up the function values evaluated at the xi's, which leads to 1.85, 26, 179. Substituting this into the approximation C4, we get for n equals 4, we will estimate the theoretical upper error bound. The global error term becomes, which leads to, where the cosine term will vary between 0 and 1. So to find the maximum possible error, we replace this term with 1, which yields 2.32262. The true error is in fact much smaller than this value. The Gauss-Chebyshev estimates of the integral and the corresponding true absolute error for various n values from 2 to 10 are tabulated. Note that the calculated estimates depict improvement for increasing n and tend to converge to the true solution. For n equals 8, the true error of the order of 10 to the minus 6 was realized, which is less than the predicted upper error bound for this approximation. For n equals 10, the true error of the order of 10 to the minus 9 was achieved, which is also less than the predicted upper error bound. With this note, we conclude our lecture. That is all for now. See you next time with another topic. Bye.